If you divide this like this, you have one loop over here, which is in the YZ plane. So if you use the right-hand rule, the magnetic dipole moment will be in the X direction. Now the magnetic dipole moment, the magnitude of the magnetic dipole moment is always defined by, well, not all. This is the definition if the loop lies on a plane. This definition you cannot use over here for this loop because it doesn't lie in a plane. But nevertheless, you can still divide this into two loops lying on a plane, and one is in the YZ plane, so its magnetic dipole moment, if you use the right-hand rule, it will be in the X direction, and its magnitude is nothing but the current running through it times its area, which is pi r squared over 2. So this is the contribution to the total magnetic dipole moment due to this one. Now the other contribution will be from this semicircle on the XY plane. Again, if you just use the right-hand rule, the magnetic dipole moment will be in the Z direction. And its magnitude will still again be the same because it has the same area, the same current is running through it, so it is I pi r squared over 2. So this is the total magnetic dipole moment. Now, if you put this in a magnetic field, you can use this magnetic dipole moment to calculate, for example, the torque acting on this system. So it doesn't matter which shape it has, you already know the magnetic dipole moment, so you can calculate the torque acting on it. Or if you would like to find how much magnetic field this creates at a faraway point, again, you just use this magnetic dipole moment and calculate an approximate value of the magnetic field that this dipole creates at a faraway point. Well, it doesn't really make any difference. You can still divide it into two parts. Of course, the areas will be different in that case. You will use different areas, but the logic will be the same. This is the direction is just something like this. No, it has two contributions. Okay. Why? Well, you see, the right-hand rule is valid only for closed loops lying on a single plane. Now, this whole thing isn't lying on a plane, so you cannot really use the right-hand rule for this whole thing. But you can still use the right-hand rule for parts of it. You can use the right-hand rule for this semicircle, and you can use the right-hand rule for this other semicircle. So each one gives these contributions. The total magnetic dipole moment will just be the sum. It's just like the electric dipole moment. If we had a system of not two charges but many charges, you just divide it into smaller dipoles, electric dipoles, and you just sum the electric dipoles. In this case, you just sum the whole system into smaller parts whose magnetic dipole moment you can calculate using what we already know, and you just sum them up to calculate the total magnetic dipole moment. Any other questions? Any questions about the thing that we had done today? Okay, so if you just review what we had done since the beginning of the semester, we started about discussing the electric field. The sources of the electric field was point charges. Then we discussed the magnetic field, and we said that the source of the magnetic field are moving point charges. Now we have an alternative source to an electric field. And it is the changing magnetic field. It also creates an electric field. Changing magnetic field creates an electric field. Now, how to see that? So let's look at this, the Lenz force, Lorentz force is Q E plus V cross B. Now, if you remember when we were first discussing this Lorentz force, I was mentioning some kind of a contradiction in the sense that suppose we have a region where we have a uniform magnetic field and then we had this point charge plus Q, let's say, moving in this direction. What will be the force acting on it? So there will be a force acting on it in the upward direction. There's no electric field in the system. There's only a magnetic field. The charge has some velocity. So this is 0. It has a velocity. There's a magnetic field, so it will feel an upward force. Now then we said, okay, let's go to a reference frame in which this charge is at rest. It's not moving. We just sit on it, let's say. If it is not moving, then there is no magnetic force acting on it. Nevertheless, there should be some force on it because the acceleration is independent of reference frame. If you are in one inertial reference frame, if you measure one acceleration, if you go to another inertial reference frame, you should measure the same acceleration. But at least if we just apply this straightforwardly, it doesn't seem to hold. In the sense that in one reference frame, in this reference frame, the charge is moving with a velocity v. It feels a magnetic force in that direction. It will be accelerating upwards. In the other reference frame in which it is at rest, so let's just consider the other reference frame in which the particle is at rest. V is 0, and it should still feel the same acceleration. But if it is feeling the same acceleration and V is 0, it cannot be due to a magnetic field, because the magnetic force is proportional to the velocity, the speed. If the speed is 0, there is no magnetic force. But since it's still feeling a force, it just means that there is an electric field over there. There should be an electric field in this new reference frame. Now the question is, where did this electric field come from? It's not the electric field of this point charge, because the point charge cannot feel a force due to its own electric field. It should come from somewhere else. Yes, the magnetic field is moving. So that is mainly the source of the electric field. Which one? No, okay, you see, in this reference, the physics is independent of reference frame. Whichever reference frame you choose, whichever inertial reference frame you choose, you should see exactly the same thing. And I have this reference frame. And when I look at my system in this reference frame where there is no electric field, there's only a magnetic field, what we see is there is a force acting on it. And it's accelerating. So this conclusion about the nature that there is an acceleration should be independent of which reference frame I choose, which inertial reference frame I choose. In every inertial reference frame, it should have an acceleration. If nature is independent of reference frame. And that's what we believe. The choice of the reference frame is a human choice. Nature doesn't choose a reference frame. So it should also, if it has an acceleration here, it should also have an acceleration in this reference frame. But in this reference frame, it cannot feel a magnetic force. It can only feel an electric force because the velocity is 0. So there's an electric field in this reference frame. Now then the question is, what is the source of this electric field? As your friend pointed out, in this reference frame it's the magnetic field lines that are moving. And actually that is what creates this electric field. So since the magnetic field lines are moving, we have changing magnetic fields and which create this electric field. I mean, exactly. The changing magnet. I mean, up to now we said that, okay, if we have this conducting loops, if it's moving in a magnetic field, then there will be a current running through it. But why? Now, okay, we said one thing. We always discuss this conducting ring moving in a magnetic field creates the current. But we can look the other way around. We can consider a magnetic field moving in the reference frame in which this conducting loop is at rest. So we should see the same current, exactly the same current. Then the question is why? What creates that current? Okay, in one reference frame we said that, okay, since this rod, in the rod example, since this rod is moving, the charges in it are moving, so electrons will feel a force, and since electrons are free to move, they will move, and hence create the current. Now in this other reference frame, the rod is at rest, so it's the magnetic field that is moving, but since the rod is at rest, the electrons can only feel the electric force, not the magnetic force. So these moving magnetic field lines should be creating an electric field, which creates this current, if we want our framework to be consistent. Otherwise, physics will depend on the reference frame, which is not something that we want. Physics should be independent of reference frame. And the only way we can achieve this independence is if we accept that the changing magnetic field creates an electric field. Well, you see, in this Lorentz force, it is not the relative velocity appearing over there. It is the velocity of my object measured in that reference frame that appears in this Lorentz force. It's not the relative velocity. We can't, because we are, and this is zero. Why would you like to apply the right-hand rule? Zero doesn't have a direction. There should be an electric field. In fact, the direction of the electric field should be pointing upward. It's not out of nowhere. We are just identifying a new source of electric field. And before we said that the electric fields are created only due to point charges. That was our only source of electric field. Now we see another source of electric field. This changing magnetic field lines should be creating an electric field. Otherwise, this, as you said, this mathematical trick will changes the physical result, which shouldn't be. Yes, and this mathematical trick tells us that if changing magnetic field doesn't create an electric field, this mathematical trick tells me that in this reference frame my charge will be accelerating, in this reference frame my charge will not be accelerating. If changing magnetic field or moving magnetic field lines do not create an electric field, then in this reference frame there is no force, which shouldn't be. Yes, more or less. Now, okay, in that case also, we went to the reference frame in which the magnet was at rest to discuss the problem. Because our previous knowledge only applied in that reference frame. Now, this would allow me to apply the same principle in this new reference frame. Because now I know that since as the magnet is moving, I have a changing magnetic field everywhere. Since there's a changing magnetic field, there should be an electric field in that reference frame. Since there's a changing magnetic field. If there's an electric field, it will create these, that electric field is what creates these currents in the tube. And this one? No. You just choose a reference frame, one reference frame. In that reference frame, you might get some electric field, some magnetic field, and this will be the force acting on it. And in that reference frame, you have the velocity of your object. Then you might go to another reference frame. Okay, in this new reference frame, this argument actually tells us that you have a new magnetic field, you will have a new electric field, you have a new velocity. And this new electric field and new magnetic field in this new reference frame should be such that the force in both reference frames are exactly the same. No, hold on. I'm not saying that these two systems have the same electric field. True. This is for this system. Okay. Now, what I'm saying is this. Well, we are actually both saying the same thing. You and I hope everybody else here agrees that whether I'm in this reference frame or whether I'm in this reference frame, the charge should be accelerating upward. That shouldn't change. Now, this charge can feel two kinds of forces, an electric force and a magnetic force. And historically, we have defined them in this form. There is a force that this charge will feel, which will be independent of its velocity, which I call the electric force. There is another force which depends on the velocity of the charge, which I call the magnetic force. So I make this observation. I look at this in this reference frame. I see that my object there is a uniform magnetic field. My object is moving in this direction, V, and it will feel a force in that direction, F, and the electric field is 0. That is my observation. Then you, more energetic, you run with the charge. So what will be your observation? Okay, we both agree that in your reference, we should both measure the same acceleration. Okay, there's no question about that. We should both, if a mass is accelerating in that direction with some acceleration, whether I look at it or you look at it, it should be accelerating upward. But you see that for you, the particle is at rest. It's not moving. So it feels a force, which is upward, but it feels a force even if it's at rest. And according to this definition of the electric force, the force that it feels at 0 velocity has to be an electric force. So that is what, so you are making an observation. You are observing an electric field over there. You cannot really say anything about the magnetic field, but you can still say that there should be an electric field there because you have a charged object which is feeling a force, and you are a charged object at rest which is feeling a force. So with your observation, whatever detector you use, you should be observing an electric field. There's an electric field. Now the question is, what is creating that electric field? Well, you see, what do you mean by the velocity of a magnetic field? Okay, when we talk about magnetic field lines and we treat them as if they were physical objects, but what does it mean? It doesn't really mean much. It's just a mathematical tool that we invent. So you cannot really redefine this as the relative velocity. How do you measure the velocity of magnetic field lines? You only measure the magnetic field at a given point. How do you measure its velocity? I mean, in this one it is kind of easy. I'm already telling you that the velocity of the magnetic field lines in this reference frame is 0. How do you know that? If you accept this description, then of course I can define the velocity of the magnetic fields here, etc. But how do you measure it in the first place? I mean, if you cannot measure it, what's the point in defining it? So that's why we don't change this definition. We stick with this definition. But of course, if we stick with this definition, we have to accept the fact that in one reference frame, where the magnetic field is uniform and the electric field is 0, in another reference frame, there should be an electric field there, a non-zero electric field. It should be there. Otherwise, our description of nature will depend on the choice of the reference frame. Well, the electric field can do work. Well, let's see. Now, the problem is, this is at this instant. So, first question, does this charge keep moving forward or not? On a straight line, is this charge is on a wire, so that it just keeps moving on the wire? Because if so, then you will be, in one reference frame, you will have to exert some force on it, which will be doing the work. In the other reference frame, you can just describe that force. You will probably need to exert a larger force, and then there is the electric field doing some additional work, etc. But I mean, I'm not talking about all the forces, I'm just talking about the magnetic force here. But there might be some other forces acting on this charge which will cause it to move along a straight line. I don't know. I mean, you have to give me a specific example, specific motion, then we can discuss what happens in which reference frame. But electric field can do work, magnetic field cannot do work. This doesn't mean that the electric field does work. By the way, at this instant, so at this instant it will be accelerating upwards, so electric field will be doing work over here, but it's not, the magnetic force here is not doing work. But in any case, kinetic energy depends on which reference frame you are looking at it. The work depends on which reference frame you are looking at it. So the work done in this reference frame need not be the same as the work done in this reference frame. No, they don't have to be. Physical observables, yes. But what do you measure? Do you measure the work, the change in the work? And you see, the work is a frame-dependent object. If you look at the object, the work calculated in different reference frames, you will calculate different work. So, in this one, there is no work done on the object. In this one, there is work done on the charge. So what? There are two different reference frames. Energy, you see, mechanical energy is potential energy plus the kinetic energy. Well, the kinetic energy depends on the reference frame. So mechanical energy is a reference frame dependent object. So you see, if you were moving in that direction with some velocity, and when I look at you, I will see that you have some constant potential energy. You're not changing your height, but you have a kinetic energy. If I start moving with you, you have the same potential energy, you have zero kinetic energy. Mechanical energy depends on the reference frame. But the change in the mechanical energy is always equal to the change in the force done by other forces, the work done by other forces. This equality always holds in every reference frame. Now, we will discuss the waves later on. Now, the force is always perpendicular to the displacements. You see here the V, you can just think of V as the very small displacement. The force is always perpendicular to the displacement, so that's why it's not doing any work. So if you just hold this object, move it like this, I'm not doing any work because the displacement is perpendicular to the force. Now, which magnetic flux? Okay. Okay. I didn't understand your question. You see, not all quantities are frame independent. Quantities can change depending on which reference frame you are. Like the work done. The work is a frame dependent object. But there are also other quantities which do not depend on the reference frame, such as the acceleration of an object is independent of which reference frame you are looking at it. So, in one reference frame, okay. So it might be that in one reference frame you have one magnetic flux, one electric flux. In some other magnetic reference frame you have a different magnetic flux and different electric flux passing through an area. So what? It just tells me that they are not frame independent quantities. Does this bring a contradiction? So for example, we know that the work done is frame dependent. We know that the mechanical energy or the kinetic energy is frame dependent. So they will change. But what will not change is that the work done in a given reference frame, the work done on an object in a given reference frame, will always be equal to the change in its kinetic energy. This will not change. And similarly for the acceleration, or let's say for the Lorentz force. It might be that in one reference frame we have zero electric field and some magnetic force. In the other reference frame we have zero magnetic force and non-zero electric force. So what? The thing that shouldn't change from one reference frame to the other one is the acceleration of the object, or that is the force acting on the object. That shouldn't change. That's not an inertial reference frame. I would rather stick with inertial reference frames. No, it does not. You see, the change in the energy is equal to the work done. But the change in the energy of a given system is frame dependent itself, because energy is as a frame dependent quantity. So the work done is a frame dependent quantity, fine. So in one reference frame, the work done can be 1 joule, so the change in the energy will be 1 joule. In another reference frame, the work done will be 5 joules and the change in the energy will be 5 joules. So energy conservation holds. Sorry? No. Energy is a frame-dependent quantity. It changes from reference frame to reference frame. So let's see. Let's look at this one. Elevator. You go to the elevator. You hold your book and go to the 4th floor. In your reference frame, the book is not displaced at all. You have not done any work. Fine. You don't see any change in the height, so there's no change in the gravitational work also. Let's go to an outside observer. I'm just looking at the elevator from outside. What I see is you exert a force in that direction, the book is displaced in that direction. You are doing work on the book. Its potential energy is also increasing. Energy is conserved in both cases. In one of them, zero work, zero change in the energy. In the other reference frame, some positive work and positive change in the energy. Okay, you have to learn to live with the fact that changing magnetic fields creates electric field. Okay, other questions? Well, it depends on how the magnetic field is changing. And if it stops changing, electric field will go to zero. It depends on the change in the magnetic field. The change in the magnetic field will create electric field. If this change gets larger, the electric field will get larger. If this change gets smaller, the electric field will get smaller. Sure. No, I mean, hold on. A moving object doesn't create an electric field. We are just changing reference frames from one reference frame to another reference frame. Okay, if you buy the argument that in this reference frame the electric field lines are at rest, in that case, in this reference frame the electric field lines will be moving. And this will be moving at constant velocity. And if they are moving at constant velocity, they will be creating an electric field. Which one? Now, I'm not thinking of the well, this is just a sketch. The magnetic field lines are not things that exist. It's just the way we sketch certain things. We show certain things. Okay? So, I'm not saying that the magnetic field lines, or moving magnetic field lines are sources of electric field. I'm not saying that. What I'm saying is, using this sketch, or argue that changing magnetic field creates changing electric field. I'm not saying that the magnetic field lines are creating the electric field. I'm saying the changing magnetic field is creating the electric field. And this electric, you will just see in a moment that this electric field lines are also non-conservative. Since there are no charges anywhere, we already said that the electric fields start on charges and end on charges. Here there are no charges around. So these electric field lines should form circles. They should close on themselves. Why should it be? It's an electric field. But the electric field lines of this electric field form closed loops. Now, okay, so first let's agree on the fact that changing magnetic field creates an electric field, and then we can consider whether we can treat one as the other one or not. Then next week, or the week following week, I will also tell you that changing electric field creates a magnetic field. But that is for, and after we discuss that one, you should repeat your question. Now, at this level, you can ask me, were your question as, can we treat the electric field as a changing magnetic field? Well, if you just take a point charge, there's no magnetic, at rest, there's no magnetic field over there. There's no changing magnetic field, there's only an electric field. So I cannot say that electric field is changing magnetic field. It's not always true. Well, the inverse, as I said, let's first discuss the fact that changing electric field creates a magnetic field. Other questions? You still don't look happy about this fact? Let us do an example. Let's imagine we have a solenoid. This is our solenoid, and that is how we create this uniform electric field, uniform magnetic field. And the current is running in this sense. So the magnetic field is pointing out of the screen everywhere. This is the magnetic field lines. And what is the magnetic field intensity? Do you remember? Mu rho I n. N being number of turns per unit length. Now let me take such a circle. Okay, so I will first say that there will be electric field lines created. Furthermore, those electric field lines will be circular. Why? I mean, we will be changing the magnetic field. So what are the possibilities for the direction of this magnetic field? We again have the symmetries of the problem. First of all, if we rotate our solenoid, nothing changes. So should be true for the electric field lines generated by this changing magnetic field. So if I rotate my system around the axis, these electric field lines should not change. That is one thing I know. Furthermore, there are no positive or negative charges in my system. Everywhere is neutral. So electric and magnetic field lines, they cannot start at any point, or they cannot end at any point. So that's why I don't like the saying that the moving magnetic field lines are the sources of electric field, because they are not. They do not start on the magnetic field lines. The electric field lines only start and only end at charges. Now here I should imagine some electric field lines that are symmetric on the rotations around the central axis of my cylinder. Furthermore, they shouldn't start or they shouldn't end at any point. They should either go to infinity, come from infinity, or they should close up. No. The only possibility I have are just rings. They have to be rings around the central axis. So this is one possible choice of my electric field line. Now you can just choose whichever positive direction you like. Let's just choose this one as the positive direction. Okay, this is my ring. It's a ring around the center of the cylinder. And let's say that its radius is large r. Now, what do we know? We know already the Faraday's law. It should still hold for this system. We know that B dot ds, d by dt minus of this one, or let me write it in this form. This is what we know. The EMF around any closed loop is always equal to minus the rate of change of the flux that goes through the loop, in between the loop. Now, the EMF is nothing but the integral of the electric field, again around this loop, which should be equal to minus d by dt, the integral of the magnetic field over the area bounded by this loop. So what should be the direction of ds? What would you like to choose? Okay, let's just choose the direction of ds as pointing inside. So my loop, what is the orientation of my loop? Clockwise, counterclockwise. Use your right-hand rule in the direction of ds, so the loop should be counterclockwise. So this is the direction of the loop. Now, electric field and dl, let's say E is E in the theta hat direction, dl is dl in the theta hat direction. I just say that theta hat direction is the direction of dl. This is how I define the theta hat direction. I know that the electric field should be either in the direction of theta hat or opposite to that direction. I don't know which one. I don't know whether E is positive or negative. But since it's a circle, and this dl is on the circle, E and dl, they are either pointing in the same direction or in opposite directions. That I know. So E dot dl around this loop is nothing but E dl. Well, I already said that if we rotate our cylinder around its axis, the magnitude of the electric field shouldn't change. The electric field shouldn't change, so the magnitude shouldn't change. So E is just a constant. So this is equal to E. I can just take it out. What remains is nothing but the circumference of this ring, E times 2 pi r. This is my E dot dl. Now let's look at the flux. According to our choice, ds is pointing into the screen, B is out of the screen. They are in opposite directions. So B dot ds is minus B times ds, the magnitude. B is uniform, it's just constant, minus mu 0 I times n. What remains is nothing but the area, which is pi r squared. So E times 2 pi r, again Faraday's law, should be equal to minus d by dt minus mu 0 I n pi r squared. These minuses, they become plus, r cancels, pi's cancel. So the electric field has the magnitude mu 0 n times r di by dt over 2. There should be such an electric field. Well, it's a disk. This is the area of the disk. No. I mean, if you imagine a sphere, the sphere has a surface area of 4 pi r squared. This is just a disk. Disk has the area pi r squared. Okay, we will review this in the beginning of on Tuesday. You should read chapter 29. I didn't give you any pre-report on this chapter because you had the exam, but I do advise you to read it. Convince yourself that changing magnetic field creates an electric field. Any last minute questions? I mean, changing electric field creates also a magnetic field, but we will discuss it later on. Not yet. So see you on Tuesday.